Yeah, okay. So let me just start by elaborating on some of the issues that we were discussing after the end of yesterday's lecture in the discussion session. I realized that perhaps we'd not been totally clear about what we had shown and what we had not shown. And so I just wanted to start by reviewing briefly what it is that we have shown and what it is that we have assumed, just so that everyone is on the same page regarding that. Let me just make two columns. So what it is that we proved and what it is that we did not prove. Okay. So what we did prove is that, we had some arguments in ADS, but in flat space, what we did prove is that if we assume, so it's an assumption that the full UV theory shares some low energy properties of the low energy theory. Okay. So shares some low energy properties. Those specific low energy properties that we were looking for was that these operators that act on the vacuum manifolds, so in particular, these operators that we call TSS prime, that these operators continue to be a part of the algebra near the past boundary of future null infinity. We can see that in the low energy theory, these operators are part of the algebra and the past boundary of future null infinity. And then we have to continue to assume that in the full ultraviolet theory, which we don't know, that this continues to be the case. And second, we also assumed that, we also needed to assume at some point that the Hamiltonian of the full theory, so this is assumption 1 and this is assumption 2, that the Hamiltonian of the full theory has a real spectrum which is bounded below. So this is effectively an assumption of unitarity, because we are assuming that the Hamiltonian of the full theory has a real and bounded spectrum, bounded below. Under these assumptions, the place where we needed this assumption was when we said we could squeeze the Hilbert space down. When we said we could do that, we assumed that the spectrum of the Hamiltonian was positive, and we also assumed that it was real, that the Hamiltonian was a Hermitian operator in the full theory. So there was a way in which you could describe unitary time evolution. If you assumed that this is the case, under these assumptions, what we did show is that the information at I plus minus, okay, all information about the state is at I plus minus. So all information about massless particles okay. So this was what we showed, and these were the assumptions that we had. But there are some things that we did not show. Okay. In particular, we did not show that the full UV theory is well defined. Okay. So we did not show that the full UV theory is well defined. There's another thing that we didn't show, which I alluded to yesterday when I said that we didn't prove that the S matrix was unitary. You see, we've been discussing the past boundary of future null infinity. But of course, as I said at the beginning, there's an analogous story you could make about past null infinity. And if you made the story about past null infinity, the statement then would be that all information is available near the future boundary of past null infinity. So we also did not show that information at I plus minus is the same as the information at I minus plus. So if we had shown this, this would have been a proof of unitarity in the bulk, but we didn't make this proof. And we also didn't, prove these assumptions, although they're plausible assumptions if we believe that effective field theory continues to work. If effective field theory works and there's a good ultraviolet completion of the low energy theory that we see around us, then we don't expect that ultraviolet completion will change the properties of low energy physics. And we assume that, if there is a UV completion, that the formalism of quantum mechanics will continue to hold, and therefore there will be, a real Hamiltonian, which doesn't lead to a sick theory with an unbounded spectrum, which is unbounded below, but has some lower bound in the spectrum. Okay? So we needed to make these assumptions, and under that we found this interesting result about how information is localized. But I want to emphasize that we don't have a proof of unitarity. Now, this attitude that we have taken is actually also the attitude that is taken in many other discussions of information and quantum information about black holes. It's the attitude that, let's assume that there is a well-defined UV theory of quantum gravity that has some nice properties. And then let us check whether these puzzles that we have about black hole evaporation can be resolved within that context. Or, if we still find that there's a puzzle, then we need to think harder about that UV theory of quantum gravity. And the benefit of taking, and this is an approach which I think is quite consistent in large parts of the literature, and the benefits of taking such an approach, I think, are that this kind of an approach teaches us interesting lessons about quantum gravity. To give just one example, we spent several lectures discussing the past few lectures discussing this thing that we call the principle of holography of information. But as I described at the beginning of yesterday's lecture and also previously, this is something that we arrived at because we were thinking about black holes. And so it is by a careful consideration of black holes that we arrived at this principle. But in the end, the principle also has low energy consequences. Right? So the advantage of this approach is that it leads to lessons, and it leads to lessons about low energy physics that maybe we would have arrived at even otherwise, but that we arrive at by thinking carefully about black holes. And in particular, this principle of holography of information, I think, is interesting because even though we were joking about astrophysicists, and I was drawing these cartoons of astrophysicists, in principle, one could imagine, not with current technology, but maybe one could imagine a very clever experiment in which you could try and ask these questions about quantum gravity, because what we need to measure is a 2-point function, and making such a measurement would be much easier than making a measurement about all the information in black holes. So this leads us, in principle, this principle of holography of information and the low energy test that we described previously gives us some interesting physical consequences of quantum gravity, some of which might be relevant at complexities well below the question of, is full black hole evaporation unitary? Which also we might be able to check if we found a way to simulate black holes, or, make up black holes in condensed matter systems or something like that. But before that, we already have an interesting consequence about how quantum information is localized in quantum gravity. And that comes from a consideration of black holes. So I just wanted to say that this attitude is interesting because these assumptions, we put in some assumptions, and those assumptions lead us to interesting lessons about quantum gravity. Okay, and of course, it should be clear that at no point have we proved that the theory of gravity in flat space is unitary and well defined, or that we have a complete theory. And that's that would be something that would be much harder to do. It could be, for instance, that the theories we are considering are in the swarm plan. For instance, yesterday we discussed theories which have global symmetries, and it is believed that theories with global symmetries, cannot be completed into good theories of quantum gravity. But we don't see that in the low energy physics that we're exploring. So I wanted to emphasize once more this table is that we make certain assumptions. And this assumption, gave us something which I think is already interesting. This is an interesting consequence of these assumptions. It's some very interesting fact about how, I think, an interesting fact about how information is localized in gravity. But we haven't proved any of these things about the full UV theory being well defined, or even that gravity, the S matrix, is completely unitary. And the advantage, as I said, is that it leads us to broader physical lessons that apply even in the absence of black holes. Okay, so that was just one clarification I wanted to make. I guess maybe because not everyone was there at the end of yesterday's discussion, and I wanted us to be all on the same page about what we were discussing. Okay, I don't know if there are any comments on this. We can, if there are brief comments, we can take it now or again in the discussion later today. Okay, so let's return then to a consideration of the monogamy paradox, which is the paradox that we discussed yesterday. So let me just remind you what we did yesterday. We considered empty ADS and we set up 3 regions inside empty ADS. These were the 3 regions that we had. We just took some point in the middle of empty ADS, which we called, or some sphere in the middle of empty ADS at some radius r0. We looked at the region outside that sphere. We looked at the region just inside that sphere. The region just outside was called A. The region just inside was called B. And then we looked at the region far away. And we showed that in the vacuum, it was possible to find operators so that CAB is greater than 2. But it was also possible to find operators so that CAC is greater than 2. And this violates the monogamy inequality because this tells us, of course, that the resolution to the paradox was just that these operators that we thought were localized in A and B were not really localized, because you had to have a Wilson line that dressed every operator in A out to C, and you had to have a Wilson line, a gravitational Wilson line, that dressed every operator in B out to C. And therefore, it wasn't really the case that these operators that we thought were sitting inside A and B and would commute with all operators in C, they didn't really commute. And if you started to look closely, you would find, you would find yourself in trouble. If you were to insist that information in gravity is localized the same way as it is in quantum field theories, you would end up with trouble, as we did here. Okay. I want to just follow up very briefly on this by saying that this is a paradox that we constructed about empty space. It's possible to construct a very similar paradox also about black holes. About black holes, we'll have to be a little less explicit because we'll find that some of the operators involved are very complicated and we can't write them down, although we have an existence proof. But I just wanted to demonstrate that briefly, how, if you were to insist on making this kind of an error, we could also end up with a paradox about black holes. So let me go back to the setting of black holes. And once again, we have some singularity and maybe some matter and so on, but we don't really care about that. Here is a horizon. Here's a Cauchy slice. This is the region A, B, and this is the region C. Okay. In fact, this is the framework in which we originally set up the the monogamy paradox. So now in this setup, when we set up the monogamy paradox, we first argued, so say the black hole microstate is psi. So let's again be in ADS. We can think of an ADS black hole. If you like, we can think of a small ADS black hole that's evaporating. We are not going to need any details of this black hole microstate because the result that we'll find is rather general. So say that the black hole microstate is psi, then of course what we argued was that without knowing details of this microstate, if we know that the metric in the bulk is smooth, then we expect that CAB is larger than 2, or we can construct operators A and B. I won't write them down again explicitly, but we can construct operators inside A and inside B, so that if you look at this CHSH operator, which is A1 into B1 plus B2, and so remember that the definition of this was this kind of an operator. And we had to pick these operators A1, A2, B1, and B2, and we could pick them by projecting onto states of the radiation outside and the partners of the radiation inside. And using this, we were able to construct these operators so that CAB was larger than 2. And this is just a reflection of the fact that the outside of the black hole, the region outside, is entangled with the region inside. And now I want to show you how even in a black hole background, one can find operators in C, or one can argue for the existence of operators in C, so that one will end up with the violation of the monogamy paradox. Once again, in this case, we won't be able to write down the operators explicitly, but we'll be able to argue for their existence. And in fact, when the original monogamy paradox was set up about black holes, if you will recall, it was only done by arguing for the existence of complicated operators in C that needed to be entangled with A. And we will now use a different existence argument to argue for the existence of operators in C that will be entangled with A, and we'll show that there'll be a violation of the monogamy inequality, in fact, even before the black hole has entirely evaporated. So the argument is quite simple. Remember that we can find, okay, there exist operators which have the following properties. Okay. Q on psi, Q acting on the vacuum gives you psi. Q acting on B1, or there's another operator QB1, which gives you the action of B1 on psi, which I'll denote by B1. Okay. And there's another operator which I'll call QB2, whose action on the vacuum gives you the same as the action of B2 on psi, which I'll denote by the state B2. Okay. So the existence of these operators follows from the argument we made in the beginning, or several lectures earlier, which was that if you're given the vacuum and you're given a set of operators near the boundary or in some small time band in the boundary, then you can act on the vacuum with such operators and create arbitrary states in the theory. Of course, one can write down explicitly the form of such operators for low energies. In fact, we have some assignment questions on this, which might be useful. But when you have black hole states, you can't write down the existence. You can't write down such operators explicitly. They're very complicated operators, as you expect they should be. But we still believe that they should exist if the theory makes sense under the assumptions that we outlined previously at the beginning of this lecture. And so there should exist operators in far away in this region C, so that when they act on the vacuum, they can create these states psi and B1 and B2. Okay? Now, remember, of course, that the projector on the vacuum even here lives inside C. And therefore, you can write down the following kind of operators. You can write down the operators Bi. So, by the way, B here, this B here is the operator that appears here. So it's the same operator that appears here. It's the operator that we used that was entangled with the Hawking modes outside. So we wrote down an operator in effective field theory which was entangled with the Hawking modes outside. It's the same operator B that's appearing here. There are actually a QB1 and a QB2, and there are two operators here. And so when I use the index I here, like this index I, this I can run over either 1 or 2. And so we can write down this operator, which causes the transition between psi and the state B1, just as this. And you can check that if you expand out the projector on the vacuum, you will find that this operator turns into Bi psi, and this belongs to C, because all these operators belong to C. This belongs to C, this belongs to C, and the projector on the vacuum belongs to C. Of course, I emphasize again, this is a very complicated operator, and it has to be complicated because we do expect that operators outside, far away that can probe black hole microstates will be very complicated. So it's much more complicated than the empty space operator that we wrote down. And similarly, I can write down also operators of this kind. I can write down the conjugate of this, the Hermitian conjugate of this operator. I can also write down operators of this kind. And I can write down the projector onto the state psi, which is just QP0 Q dagger. Okay, because Q on 0 creates the state psi, therefore QP0 Q dagger is the projector on the state psi. Okay. If you do this, you can check. There's some algebra, which once again we'll give in homework, but it's some trivial algebra, that if you were to write down this operator, which is just a linear combination of the operators below, of the operators above, sorry. If you write down, and I have to divide this by where expectation of Bi is a C number, which is just psi bi psi, and same for expectation of bi squared. So we have an operator which we've written down here. This is this operator Ci, and you can check actually that this operator has bounded norm, and it has the property that Ci acting on psi is the same, produces the state Bi. So you can check, in fact, that if you act with the state on psi, from here you get 1 and you get the state Bi, you get some other contribution from here, and this term is designed precisely to cancel off that contribution. So that Ci acting on psi gives you the state Bi, even if Bi and psi are not orthogonal to each other. And therefore, we find that Ci on psi is Bi. And therefore, if you were to construct this CHSH operator as A1 into C1 plus C2 plus A2 into C1 minus C2, you would find that the expectation of CAC in the state psi is the same as the expectation of CAB. Okay. And I hope you see that, and that's because if you expand this out, you get psi into A1 into C1 plus C2 psi plus dot 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 plus another term with C1 minus C2. And of course, C1 on psi is the same as B1 on psi, and C2 on psi is the same as B2 on psi. And therefore, this is just the same as psi into A1 into B1 plus B2 on psi. Okay. So this is equal to, let me write down the second term. So we have an equation. And this is just equal to psi into B1 plus B2 on psi plus psi A1 into B1 minus B2 on psi. Okay. And that just follows from this equation. Okay. This equation on top tells you that this line is the same as this line. Okay. And therefore, if you believe these second two lines, you see that this is also the case. And since we proved that CAB was larger than 2, we clearly are in trouble because we find that CAC psi squared plus psi CAB squared is greater than 8. Okay. So this tells us that if we insist on assuming that the Hilbert space in the presence of gravity factorizes as it does in local quantum field theories, we end up with paradoxes in empty space about black holes before the page time and after the page time. And so it is not surprising that upon making this assumption, we ended up with a paradox with the monogamy of entanglement. Okay. Once again, to say, this doesn't prove that the interior of the black hole is smooth. If you remember, the paradox for this monogamy of entanglement was constructed to advocate for fuzzballs and firewalls. And what we have shown right now doesn't prove that fuzzballs and firewalls don't exist, but it tells us that this monogamy paradox cannot be used to argue for the existence. We will, in fact, in later lectures, discuss some other arguments that might, that could be used to argue for their existence. But this monogamy paradox just tells us, something that we should expect in a theory of gravity. So that's all I wanted to say about the monogamy paradox. I now want to move on and discuss the issue of the entanglement entropy at scri-plus. If there are any questions about the monogamy paradox or about the first part of today's lecture, I can take them now.
Yeah, I have one question.
Yeah.
About the it is about the monogamy paradox in empty ADS. So we have seen that this paradox can be realized even in empty ADS. So how does, what does fireball and fuzzball proposal has to say in this empty ADS case? Because in the black hole case, one can assume that there might be a fireball, but how can we think of that in empty ADS?
No, there's no firewall or fuzzball, clearly. So the point of the empty ADS paradox is to say that, look, you have an empty ADS, you clearly don't have a firewall or fuzzball, and you're producing the same paradox. So there's no, there's no firewall or fuzzball proposal for empty ADS. In empty ADS, the resolution is completely clear. It is the fact that these operators that you thought that were localized in A and B were not localized in A and B. So you see, the only way you could now believe in the firewall in this monogamy paradox in the black hole case is that you could say that, in empty ADS, we agree that the operators that were localized in A and B were not, that looked like they were localized in A and B were not really localized. They had to be addressed with Wilson lines. But somehow in the presence of a black hole, we believe we can really localize operators anyway. So even though you're showing us clearly that you'll run into trouble in empty ADS if you assume the Hilbert space factorizes, we'll nevertheless go ahead and assume that in the presence of black holes. But once again, in the presence of black holes, if you go ahead and assume that, we can construct a monogamy paradox. So I mean, I don't think there's really a case for the monogamy paradox to be used to argue for firewalls or fuzzballs. I mean, you could say that this paradox that we have on this slide is not the monogamy paradox we found, and the operators C that we found there was somehow different. Even though we are finding one paradox, there's another paradox which has. I think it's not a tenable argument really to use the monogamy paradox, because what these toy paradoxes tell you is that if you insist on this kind of an assumption that the Hilbert space factorizes, gravity localizes information the same way as QFTs, you're bound to run into trouble. There's no firewall or fuzzball proposal in MTADS. I mean, the construction of this toy paradox is to just point out that you shouldn't assume the Hilbert space factorizes.
Okay. Yeah.
Okay. Are there any other questions? Okay. I mean, I have to say that I think this monogamy paradox is a very interesting paradox. Even though if you had thought carefully about all of these things before this paradox was proposed in 2009 or 10, it would have been, we could have thought about these issues, and we could have thought about these issues carefully even then. But we, in principle, but we didn't. And so I think it was very interesting because it forced us to confront this issue that the Hilbert space in gravity does not factorize the way it does in local quantum field theories. And so I think it was very interesting. But I think it is quite clear that the resolution to this paradox comes from the lack of factorization of the Hilbert space. As I said, there are other paradoxes that we'll discuss that are relevant for firewalls and fuzzballs in maybe a couple of lectures later, which are different. But for this paradox, I think, and this is an example of how I think thinking about black holes teaches us some general lessons about quantum gravity. Okay, great. So now I'm going to switch gears a little bit, and I'm going to talk about the issue of the entanglement entropy at scri-plus. Okay, so what do I mean by the entanglement entropy at scri-plus? For a long time, there's been a quantity that has been of interest, and which is the following. In a theory of gravity, we can talk about approximately some regions A and B and C, but in general, we know that these regions can fluctuate, and so it's very hard to define what these regions mean. And therefore, within the discussion of quantum information measures in flat space, it's been common to talk about a notion of the entanglement entropy of a segment of scri-plus. And what that means is as follows. So think of the Penrose diagram. Even in the presence of black holes, the Penrose diagram is this, because as we said, black holes evaporate. And so in the end, we believe that the Penrose diagram should be trivial. And even in the presence of black holes, we can look at some segment of scri-plus, maybe not this color. We can look at some segment of scri-plus that runs from -infinity to U0, -infinity to U0. And we can think of this, we can think of scri-plus itself as some limit of Cauchy slices as you push them up. And then we can try and ask, what is the entanglement of this segment of scri-plus with its complement? And its complement is, of course, this green region. Okay. So we can ask, what is the entanglement of the pink region with the green region? Okay. So what I want to now ask is, what does this principle of holography of information tell us about what this entanglement should be? So first, before we do that, we need to define what we mean by this entanglement entropy. So this entanglement entropy is defined as follows. It's in fact the standard definition of the entanglement entropy. So we consider the algebra of operators in this region -infinity to U0, and let's call this algebra A of U0. I'm dropping the fact that it actually runs from minus infinity. This is not the algebra that cut U0. This is the algebra that runs from minus infinity to U0 in the entire pink region. But I'm just calling it A of U0. So what this means is that I have some set of operators, and I look at I multiply them in all possible ways. And then that gives me, I take linear combinations, Hermitian conjugates, and that gives me the algebra. There's a well-defined notion of an algebra of operators from minus infinity to U0, and let's call that A of U0. Okay? Now imagine that the theory, the full theory, is in some state psi. This state psi could actually be a mixed state as well, but let me just write a pure state for now, and it's trivial to see how this will generalize to a mixed state. Okay? Then we look for an operator for rho that belongs to this algebra. Okay, so please note this definition carefully, such that which has the property that the trace of rho with any operator O is the same as the expectation value of the operator O for any operator O that also belongs to the algebra. Okay, so notice this is a definition. Okay, this definition, this operator rho is what is going to be the density matrix associated with the segment from minus infinity to U0. This is the standard algebraic definition of a density matrix. I'll explain in a minute why it's the same as the usual partial trace definition that perhaps some of you have seen. But the algebraic definition of the density matrix is this. You look for an element of the algebra that has a property that when it is traced with other elements of the algebra, it gives you the expectation value of that other element. Okay? Let me show you, for those of you who've not seen this definition before, let me try and explain why this definition is actually the same as the partial trace definition in the situation when you have a factorized Hilbert space and you can define a notion of a partial trace. Okay. So I'm now going to make a simplification, and I just want to explain why this definition of rho is the same. So imagine that you have a Hilbert space which factorizes into H system times its complement. Okay. So we have the Hilbert space in H system, and we have its complement, and the full Hilbert space is a direct product of these two. And then let's say I have some state psi in this big Hilbert space. Okay. Then the density matrix I would usually define as trace of psi psi, and by taking the partial trace over the complement of psi psi, right? But it's clear that the operator defined in this way, right, that it acts trivially on H on the complement of the system, right? It acts trivially on the complement of the system. So it belongs to the algebra of operators in H system. So the density matrix is an element of the algebra of operators in H system, and it also has the property that trace of rho with O is the same as the expectation value of O in the original state. I mean, this is the definition. This is what we demand from a density matrix, that the expectation value of O should be given by the trace of rho with O. You can check that this in fact completely fixes what rho has to be, because I've told you what the trace of rho with every other element of the algebra of operators has to be, and rho itself belongs to the algebra of operators. If I take the trace of two elements of the algebra, that defines some linear functional on the algebra, and you can check that these two properties completely fix rho, okay, for all O which also belong to operators in H-sys. Okay. So you could define the density matrix this way, which is how we usually define it, and then you would arrive at properties 1 and 2. What we've done below is that we don't want to assume that there's some factorized Hilbert space. We want to have a more general algebraic definition. So we just insisted on properties 1 and 2. And that, as you can see here, is the same as this definition. Okay? So that's the definition that we have here. And that's what we want to use to define the density matrix of this segment from minus infinity to U0. Okay? So if once we have this rho, so find rho as described. And then we compute S of U naught. So let's write rho being U naught as just trace of rho U naught. Okay. I'm being a little bit sloppy here, which perhaps some of you have noticed, because in fact, these von Neumann entropies need to be carefully regulated, and they don't really make sense in a quantum field theory. And therefore, I should really, be speaking of the relative entropy between two different states. But the result I want to show is actually a pretty simple one. And so I hope you'll allow me the sloppiness to speak in terms of density matrices and in terms of these traces and this von Neumann entropy. For those of you who are more rigorously minded and want to do things more carefully, you can very easily carry out this same argument by using a notion of a relative modular operator to define a relative entropy. But I won't do it in that way. I just wanted to use because the result I want to show is very simple. Okay. So now notice what we have. So this is the definition. This is the standard definition of the von Neumann entropy, provided you regulate this entropy correctly. So now the question is, what do we expect from this? Okay. So notice that let us say that we are in some state which is psi, and we have found an element which has the property of this algebra, which has the property that this is equal to O for all O that are in this algebra. Okay. But now remember that this operator rho of U naught is within the larger Hilbert space, some operator that takes the larger Hilbert space of massless particles back to itself. Okay. Therefore, it must be the case that we can approximate rho of U0 by an operator in the algebra near the pass boundary of future null infinity, which we've been calling A minus infinity. Okay. So this is an algebra near the pass boundary of future null infinity, which runs from minus infinity to minus 1 over epsilon. And from the arguments that we've been giving previously, for any such operator which lives in the larger algebra, you can approximate it arbitrarily well. When I say approximate, we can actually approximate arbitrarily well this operator in this algebra U0 by an operator in the algebra near minus infinity. Okay. But this means that if you now expand this interval up, you never need to change this density matrix, right? Let's say someone else comes and says, well, I have access to a larger operator, okay, some larger operator, which is U0 prime. You see that you never need to change this density matrix, because once and for all, you can pick an operator in this region, right near minus infinity, which already has the property that it gives you the correct expectation values for all operators in this on null infinity. Okay. So you see that as you expand U0 to U0 prime, where U0 prime is marked on the board, which looks like it's larger than U0, it looks like you have access to a larger set of operators. But this principle of holography of information that we have proved tells you that you don't actually have access to a larger set of operators. I realize my diagram actually runs onto past null infinity, but all the segments above are on future null infinity. And as you extend or change these segments on future null infinity, provided you have included this part that runs all the way to minus infinity, you see that you never need to change your choice of the density matrix. In a local quantum field theory, this would not be true, because it would not be true. This statement only holds in gravity. Okay. It would not be true in a local quantum field theory that you can approximate some operator from a larger cut, from a cut at different U by an operator near A minus infinity. Okay. So this tells you that the result is that trace of rho U0 log of rho U0 is independent of U0. Okay. So that tells you that if you were to compute this entanglement entropy, if you really compute the entanglement entropy defined in the way that I just defined, it's rather uninteresting. and it does something that you might find a little unexpected. It just stays constant. Okay. This one can in fact think of as a formalization of the result that we described previously, which was that the information about a black hole is always outside. And one way to formalize that result, just to remind you what the geometric setup is by saying that the Neumann entropy of the segment from -infinity to U0 just stays constant. The reason I have a finite intercept here is because of what we discussed a few times, that we have not included massive particles, and therefore even if the full state of the theory is pure within our formalism, we need to reduce on the set of massless particles, and that set of massless particles will in general be a mixed state because there'll be some entanglement between massless and massive particles, and since we haven't included that in our algebra, we expect to get some entropy that's a constant, but the entropy is a constant. It doesn't change as you go to U0. So it is not that you get information, more and more information as you go to larger and larger U0. The amount of information that you have is constant, and that is reflected in this constant entropy curve, because the entropy is indeed a measure of your ignorance, or the amount of information you have of the state. And the fact that this entropy stays constant as a function of U0 is a formalization of the fact that the information is always outside. Okay. So this is what we were saying yesterday in words, is the statement that the information is always outside. Okay. I'm going to say a few more things about this. In fact, I'll spend the rest of the lecture discussing this issue. I also want to say that, is there a question?
Can I ask a question about this?
Yeah, go on, yeah.
Okay, just probably a naive question. Why, you said that rho U0 can be approximated by an operator on the algebra at a minus infinity for any U0, but this curve that you draw seems like it is always approximated by the same operator in the algebra at minus infinity.
Correct.
So is that obvious that you can always approximate rho U0 with the same operator at minus infinity?
Yeah, because you see, I can once and for all. So let me start with U0 being very large. So let's start with U0 going all the way to infinity. Okay. So let's find once and for all some operator which has the property that in minus infinity, which has, so let's call our operator in minus infinity, which has the property that B minus infinity on O is equal to the expectation value of O for all O that belongs to this algebra U0 for large U0. Okay. So now let me, this operator B minus infinity also belongs to A of U0 because it belongs to A minus infinity, and A minus infinity, I mean, it's not actually a proper subset, but it is a subset of A of U0. Let me find this operator B minus infinity. This operator B minus infinity will continue to work as I reduce U0, because you see, as I reduce U0, at most I could have had, that I will end up throwing out some operators O. In fact, this principle of holography of information that we have proved tells us that the algebra itself doesn't expand as you expand U0 towards future infinity. But even if the algebra were to change as you were to expand U0, you see that this condition already tells you that this density matrix, this operator B that I found here, will just work for all values of U0. Because you see, it satisfies, it gives you the correct expectation value when it's traced with any operator in null infinity. And therefore, in particular, for any value of U0, I can just use this operator B minus infinity. Does that answer the question?
Yes, very clear. Thank you.
Okay, thank you. Okay, great. So this is, let me now say a few things about this. Okay, so this is a surprising result. And in particular, this is not the what is sometimes called the page curve. And so I should note here already, and we'll discuss this a little bit more in the later part of the lecture. So this is not the conventional page curve. So as we discussed, if you were to believe that the Hilbert space factorizes, you would have thought that the entropy at scri-plus follows a page curve, but the result that we find here is that this is not the page curve. Although I'm going to explain towards the end of this lecture. why this is not inconsistent with any of the perspectives that one gets from the island computation, and then we'll discuss islands and the page curve a little bit more in succeeding lectures. But let me just say a little bit more about this result that we have, and then we'll go on and talk about islands and the page curve a little bit more. Okay. So let me now say a few things about this issue of the information being outside. At least we've tried in these lectures and so far also in this lecture to keep everything very precise. But I want to take the liberty of spending about maybe 15 minutes saying some things that are perhaps suggestive and are not very precise, and so should be treated with caution. So let me just insert a note of caution. Okay. At some point, I'll write end suggestive part, and then we'll go back to saying things which are more precise. So I just want to say, I want to wave my hands a little bit and say some things which I think are interesting, which actually we don't know how to make precise. I'll explain which of the parts we don't know how to make precise. Maybe one of you makes them precise, and that would be really great. Okay. So let me say a few things about this issue of information being always outside. You see, someone could have said, we proved that the information is always outside in a theory of gravity. But this, the world is gravitational, right? We have gravity around us. So this would mean, in some sense, that the information that lives inside my computer's hard disk is, in a sense, always outside, and that clearly is not quite right? So there must be a sense in which the information that lives in the computer's hard disk in front of me is actually inside the hard disk and it's not outside. And there must also be a sense in which, if you have the evaporation of coal or some black body radiation which leaks out of a box, that there is a page curve. So this result that we have about the entropy, in some sense, maybe it's true if you make arbitrarily fine-grained measurements, that you can always find the entropy, and you always know what's inside. And the entropy, as we defined it in an algebraic approach, did involve these arbitrarily fine measurements. But there must be some sense in which, for ordinary objects, you should recover the ordinary page curve. So we do expect that for ordinary objects, and by ordinary objects, I mean not black holes, we recover the usual page curve. Okay. In what sense does this happen? So let's first just understand why this happens. Okay. Let's say that we had like some coal or something, right, which was, so let's say you have coal. So we have some coal, and we make some. So this is our piece of coal. It's evaporating, and we are trying to make measurements on this sphere which is far away. So we have observers who are stationed on the sphere far away, and they want to see what's happening in this coal, and this coal is gradually evaporating. So we would like it to be the case that for this evaporating coal, the information emerges according to the page curve. And there is a clear reason why that happens. And that is that if these observers here, our friendly observers here, wanted to use quantum gravity effects to determine what is happening inside the coal, they would need to make measurements which involve the Planck scale. They would need to measure fluctuations of the graviton. So they would need to make measurements which at least are of the order of the energy levels in the coal divided by m Planck. Okay, so they would need to make measurements up to this accuracy, which is delta E divided by m Planck, where delta E is the spacing between energy levels of the coal. If they cannot make measurements at this accuracy, they cannot use these quantum gravity effects to determine what is happening inside the coal. Okay. But what about observers who are collecting the radiation that's coming from the coal? Right? So if you just collect the radiation, those observers also need to make measurements which are very accurate. We discussed in the first few lectures how typical pure states look almost the same as thermal states, but they also need to make measurements, but they need to measure at accuracy, which is given by e to the minus s, where s is the entropy of the coal. And you can see that we can consistently take a limit where we take, we keep S finite and we send M Planck to infinity. Okay. In this limit, you see that order e to the minus s may be very small. If you wanted to determine by looking at a burnt piece of coal what the microstate of the coal was, that's something very hard, but it does not involve at any level M Planck, and M Planck can be sent off to infinity while keeping S finite. Okay. So in this sense, if you were to make measurements at this accuracy, which is e to the minus s, and you separate e to the minus s from delta E over M Planck, you see that we would, you would expect to see a page curve. Okay. So in this limit, we expect the usual notions of information localization to emerge. And this is always a sanity check that we need to do whenever we make these statements about how gravity localizes information. Unusually, we need to check that there's a well-defined limit when you start talking about ordinary objects, about qubits or computers or other things where these effects become unimportant. So it should not be the case that these effects become important in all situations. And you see here that there is a clear limit where you can separate quantum gravity effects from the accuracy that's required to make a measurement of the microstate of the coal. Okay, good. But now let's turn a little bit to black holes. You see, in the case of black holes, we have some more difficulty. And the reason is that S is in fact energy over M Planck squared, where E is the energy of Hawking quanta. Okay. So remember, in the case of coal, I said, let's take a limit where you keep S finite and send M Planck off to infinity. Let me just copy this. And then if you do that, you will find that the page curve emerges. By the way, what I said for coal is also true for what I said yesterday for these pulses of radiation. There was clearly a sense in which it was easier to detect the pulse by just going and measuring the pulse. And to use gravity, you needed to do some quantum gravity measurements, which you didn't need to do if you're directly measuring the pulse. But in the case of black holes, you see that if you try to take this limit where you send M Planck to infinity, but keep S finite so that you can make measurements at order e to the minus s, this limit doesn't exist. And it doesn't exist because the entropy of black holes has the unique feature that it actually scales with G Newton. So the entropy of black holes in the limit that gravitational effects become arbitrarily weak goes to infinity. Okay. So you see that this naive limit does not exist for black holes. And what this means is that there is no obvious hierarchy of difficulty between the following two processes, between trying to use QG effects to decipher the microstate. So you use these effects that we are describing, you measure fluctuations of the metric and other operators, and collecting the radiation. And such a hierarchy does exist for ordinary objects which don't have entropy like that of black holes, but it's not clear that such a hierarchy exists for black holes. I said that what I was saying was suggestive, and let me also point out what we have not proved. So this is the part which we have not proved. This does not prove, or maybe here, no proof that a hierarchy does not exist. So it could be that if we think more carefully about how you need to make measurements, that we find that either that we find that the right side is easier than the left side, so collecting radiation is easier, or maybe we find even that using quantum gravity effects is easier. And we've not found, there's no proof we have given that these two are at the same level of difficulty. But the only point I want to make is that because of this curious fact that S itself scales with M Planck, you can't naively take a limit where you keep the entropy of the black hole finite. So you make measurements on the Hawking radiation, which are e to the minus s. There's no sense in which those measurements are any easier to make than using these quantum gravity effects to decipher the microstate. Okay? And as I said, this is suggestive, and the reason it's suggestive is because of this fact, is because we don't actually have a protocol to reconstruct the microstate of a black hole. Okay, let me say a little bit more about this, and a little bit more I want to say comes from some intuition from small black holes. Is there a question?
Yeah.
Yeah.
I can ask a quick question. So
Yeah.
are you saying that the entropy of the coal would follow the same constant page curve that you saw before if we are able to measure it with using quantum gravity effect?
Yeah, if you define the entropy as an arbitrarily fine-grained quantity by making like arbitrarily complicated measurements, then indeed you would know what is happening inside at all times. The von Neumann entropy is actually not a very physical thing. The von Neumann entropy is an extremely fine-grained object. I think that's something that one should emphasize. The von Neumann entropy can differentiate between pure states and mixed states. And if you were to define the von Neumann entropy in an arbitrarily fine-grained manner, then indeed the entropy of the coal also would follow the same constant page curve. What we mean is when we usually talk about the entropy, we say, there's a sense in which we can define the entropy and not worry about all of these, not pay attention to these metric fluctuations or some degrees of freedom. There's a sense in which we can forget about them. And there's a natural sense, and that is that quantum gravity effects are in everyday objects. If you look at qubits and you want to measure the entropy, quantum gravity effects are irrelevant. And so if you make measurements to normal accuracies, you don't see these. But there is no such clear division between the levels of accuracy at which you need to measure the Hawking radiation and the levels of accuracy at which you need to measure these correlators of the metric with other observables in the case of a black hole. There's no obvious hierarchy, and I emphasize that this is a suggestive argument. And it's not a proof that the hierarchy doesn't exist. Does that answer the question?
Yes, thank you.
Okay, great. Let me say a little bit more about this. Okay, so I'm still on a slightly suggestive part. Let me say a little bit more about where this intuition comes from, which one can actually phrase as a precise question, although we again don't know how to answer it. Think of a small black hole in ADS. Okay. So let's think of a small black hole in ADS. Okay. So let's see how a small black hole in ADS. What's a small black hole in ADS? It's some black hole which has the property that it forms and then it evaporates. Okay, and its radius, its Schwarzschild radius, is much smaller than the ADS radius. Okay, so it's much smaller than the ADS radius, and that's why, unlike a big black hole, a small black hole actually forms and evaporates. And what we have here is a cartoon of the formation and evaporation of a small black hole. And let's think of in this setup 3 times. Okay. So T1 is the time before the black hole forms. T2 is when the black hole has formed but has not evaporated. And T3 is a late time where the black hole has evaporated. So I hope these 3 times are clear, and hopefully my cartoon is not too bad. And you can see these 3 times, which I've marked here. So I have a cartoon, and in this cartoon, I have the black hole, which was formed from some matter or some gas. At some time T1, the black hole had not formed. And then there's this long time in the middle, which I call T2, when the black hole has formed. And then there's the time T3, which is after the black hole has evaporated. Okay. This is a question, in fact, one could ask using ADS CFT purely in the CFT. So purely in the CFT, we could ask the following question. In the CFT, this small black hole corresponds to some state psi, and let's be in the Heisenberg picture. And we can ask, if we wanted to determine the state psi, using Heisenberg correlators, of various operators at a given time. So these are CFT operators. And if you give me all such CFT correlators, even at one time, I can always determine the microstate, right? I might need to measure like very complicated CFT correlators, but in the CFT, there's just no question that, if you have a state and you give me all correlators at a given time, I can tell you what the state is, if that just completely fixes the state. And so we can ask, let's determine psi using these correlators, and let's ask, how does this difficulty change? How does this difficulty change? And when I say change, as we take tau I to be near T1, or as we take them to be near T2, or as we take them to be near T3. Okay. So I hope the question is clear. The question I want to ask is, we have a state in the theory. It's a state that in the bulk corresponds to a black hole. And now I want to back construct the state by measuring some boundary correlators. And I'm asking, how does the complexity, or how hard do I need to work if I make measurements at this time T1, or at this time T2 after the black hole has formed, or at this time T3 after the black hole has evaporated? And that's a completely well-defined CFT question. We don't know how to answer it because we don't know how to describe small black holes in ADS CFT. But in principle, it's a question that we could answer given a typical small black hole state. Let me say what one would expect. So what does one expect? Let's copy this diagram. You see, at T1, we expect that the difficulty is low. Remember, what I'm trying to measure is I'm trying to reconstruct the correlators by measuring, reconstruct the state by measuring CFT correlators of the kind that I have in the box on top. And the difficulty is low. And when I say at T1, what I mean is that for tau I of the near T1, the difficulty is low. And the difficulty is low because when tau I are near T1, I'm just measuring some correlators in a gas of gravitons or whatever the initial matter was which led to the black hole formation. And that's easy to reconstruct, right? If I have like a gas of gravitons, I need to make some, maybe it's a gas of gravitons that was created with some source, but this is a low entropy state. In the beginning, the state has low entropy, and therefore the difficulty of reconstructing the state by making measurements is low. And that's what it means to say that the state has low entropy, where now I'm using entropy in the sense of the thermodynamic entropy, not in the sense of the von Neumann entropy. So this is a low thermodynamic entropy state, and therefore it's easy to reconstruct the state for times of order T1. Now for times of order T2, the difficulty is high. And the difficulty is, we can estimate how hard we need to work. We need to make measurements to an accuracy e to the minus s, where s is the Bekenstein-Hawking entropy, actually order e to the minus s. So the difficulty has gone up much more. Okay, so difficulty is high. This sense of determining the microstate of the black hole at T2 is in fact precisely the same as using these kinds of quantum gravity effects to determine the microstate of the black hole. This is the sense in which ADS CFT also tells us that information is always outside, because information always lives near the boundary. So in ADS CFT, you can always tell what the microstate is. You don't need to wait for the black hole to evaporate. You just always know what the microstate is. And this is what we should compare with using quantum gravity effects Okay, so this is the second difficulty, which is the difficulty of using the fact that information is always outside to determine the state. And it's pretty hard. It's not easy to do because you need to make these very accurate measurements. And the reason the measurements need to be to an accuracy order e to the minus s is what we discussed in the beginning. The state is part of an ensemble of e to the s states. And unless you make measurements to an accuracy of e to the minus s, you cannot tell different microstates apart from each other. They all look the same. But now the question is, what happens at time t3? Okay, so let's take this entire thing and so Let's see if I copied it correctly. I did. Excellent. Okay, I just want to keep everything on the same slide. So now at T3, of the order of T3, the difficulty is still high. It's not that the state unthermalizes. You know, how should you think of this process of black hole formation and evaporation? The way you should think of it in the CFT is that, you know, maybe you had like two gluons or two glue balls, sorry, not two gluons, two glue balls, you crashed them together, you formed a quark-gluon plasma, which was a metastable state. After some time, this quark-gluon plasma evaporated, you know, it gave you back some large set of glue balls, which evaporated. And now you're trying to ask, after this evaporation, these glue balls which have been emitted, which are the late time Hawking radiation, you're trying to back calculate what was the state of the original high energy glue balls that crashed to create the quark-gluon plasma. And you see that at times of order T3, the difficulty is still high. In fact, a naive estimate would suggest that the difficulty is of order e to the minus s prime, where s prime is the entropy of the Hawking radiation. But remember that the entropy of the Hawking radiation, by the second law of thermodynamics, you know, states don't unthermalize as you go along with time. States thermalize more and more. And therefore, S prime is actually larger than S. And so if you can see in the miniature, a very naive estimate would suggest that the, you know, if you were to try and make measurements before the black hole has evaporated, that is actually before the state has completely thermalized. As it evaporates, it's going to thermalize some more. And so if you make measurements at an earlier stage, that might actually be easier than making measurements at a later stage. Okay. Now there's a loophole, of course, in this argument. And the loophole is a potential loophole. And let me just write that down. And that's why I said this is suggestive. The potential loophole is that black holes, small black holes, are not typical states. Are not typical states. And therefore, both this estimate here, and this estimate here, maybe are not correct for small black holes. Nevertheless, I think it's very interesting that if you were to make a naive estimate of the difficulty and just use intuition from thermodynamics, the naive estimate of the difficulty, which is a well-defined question in the CFT, would suggest that the earlier you make a measurement, the easier it is just by the second law of thermodynamics. And even though after the state has thermalized a little bit after it's formed a small black hole, it is hard to reconstruct the microstate. That requires some accuracy of order e to the minus s, where s is the Bekenstein-Hawking entropy of the black hole. If you wait longer and try and collect the Hawking radiation, the state thermalizes some more. And now you might need to make measurements at an even higher accuracy, which is the accuracy of the entropy of the Hawking radiation, which is larger than the initial Bekenstein-Hawking entropy. As I said, this is a suggestive argument, but I think these arguments are interesting in that they tell us that while for ordinary objects, there is a sense in which information is not always outside. For black holes, there is a sense in which information is always outside. There's a formal sense in which you can prove information is outside, but it's not just formal. It might be a more physical statement that it might indeed be the case that it's no harder or maybe even easier to reconstruct the microstate when the black hole exists than it is to reconstruct the microstate by collecting the Hawking radiation. Okay, so that's what I wanted to say. I'm going to end the suggestive part here, and if there are questions, I can take them now. Yeah, are there questions? There's a question, yeah.
Yeah, I have two quick questions.
Yes.
The first is, what do you mean in this case for small black holes are not typical states?
Yes, they're not typical states because because of what we just said. Small black holes are special states because they never dominate the ensemble. So if you look at the microcanonical ensemble, most states are not small black hole states. So these estimates I made that, you know, the difficulty is order e to the minus s prime at late times, so e to the minus s. Those are estimates which are correct for typical states, but small black holes form up an exponentially small fraction of the microcanonical ensemble. So maybe these difficulty estimates are not correct. And maybe there is a sense in which it's easier to determine the microstate by collecting the Hawking radiation than it is by using these quantum gravity effects. So it's not like I've given you a watertight argument that it's easier to determine the state before the black hole evaporates. I just said there's some, yeah. Is there another question? Yeah.
Yeah, it was just if this difficulty is in any way related to the complexity of the CFT state, or it's just a matter of dynamics.
Is it related to? Yeah, I never know how to define complexity in a precise way. It's perhaps related in some sense to the complexity of the state, in that you could ask how many unitary operations do you have to do to go from the initial state to the later state. There's a notion of complexity, and that notion keeps increasing with time. So you could probably relate it. I never know how to make that precise, but I think it could be done. I mean, there's a sense in which they're similar.
Thank you.
Okay, great. Okay, great. So now this is, as I said, now I ended the suggestive part. So I'm not going to wave my hands anymore. And as I said, the things I said were suggestive because I pointed out a potential loophole on this slide, and also a potential loophole when we are talking about coal. Okay. But I think these are interesting issues to think about. Is it the case that it is really easier, to reconstruct the microstate by collecting the radiation or not? And when you say the information is outside for a black hole, is there a sense in which maybe the information is not always outside, or is it really physically true that the information is always outside? And that depends on this question of difficulty, which I think is an interesting question to think about. I'm not going to discuss islands today, but I just wanted to, because we are going to have a break of a week, and we will discuss islands after we come back. I just wanted to explain why what we are saying is consistent with much of the recent activity on recovering the page curve from ADS-CFT using the island proposal. So let me just describe the difference. And as I said, we won't have any details today. We'll have details later. So let me say. So what I want to describe today is a question of what it is that is being computed in many of the recent papers that have been written on recovering the page curve, and why the question that is being asked here is somewhat different from the question that we are asking. And because the questions are different, the answers are also different. And I want to explain in what sense the questions are different. So there are many calculations that have been done. But I think the original calculations and also the precise calculations that I know of, or most of the precise calculations that I know of, are done. So just to say, the summary is going to be that the question asked is different. And so the answer is different. Okay. Let me just explain what the question asked is. So the question asked is as follows. In many of the precise setups, what we do to compute the page curve in ADS-CFT is as follows. We consider a setup where you have gravity coupled to some CFTD in asymptotic ADS. So here we have a theory of gravity, and the matter sector is itself a conformal field theory. You could relax this thing, but for now, let's just take it to be a conformal field theory, which is the case where you get the simplest answers. So you have a gravity and you couple it to a conformal field theory. This is a conformal field theory that lives in d dimensions. So you have a d-dimensional conformal field theory, and you have this gravity theory which lives in ADS. And here is the ADS boundary. Okay. Now you take this entire system of gravity coupled to a d-dimensional conformal field theory, and you couple it to a bath which has no gravity. So this is a non-gravitational bath. So you have gravity on the left of this ADS, and on the right hand side you have no gravity. And then we put in here some sense in which there are transparent boundary conditions, which means that the CFT, the matter sector, the CFT in ADS, or the matter degrees of freedom in ADS, can flow from from the ADS into this region, this asymptotic region, where gravity is just completely switched off. Okay, so this is the setup that we want to ask a question about. I emphasize that here we have gravity on the left-hand side, and on the right-hand side we do not have gravity, and the matter is the same. We have the CFTD living in both setups, but there is an additional graviton here, and there is no gravity here. Okay.
I just wanted to ask, what is the dimension of the ADS that we are considering? Is it D or D plus 1?
Here, yeah. So this is just ADSD.
Okay. Okay. Thanks.
Okay, great. So maybe I changed conventions at some point. Anyway, this is, yeah, there's CFTD. So it's a matter sector. This lives in D dimensions, and there's a CFTD. The D is only going to be important in the next slide. Yeah, if you were to embed, you could embed this whole thing in one higher dimension. But for now, yeah, this is via an ADST as well.
And the geometry is smooth, I mean, at the transition point.
Yeah, the geometry is smooth. So you have ADS. I mean, you know, you go all the way out to asymptotic infinity, and then you have some other flat space. So yeah, you expect the, yeah, the geometry is smooth. You know, you're switching off gravity asymptotically far away. So the way, yeah, so let me see the next picture. Maybe that will make things clear. You see, you could take this entire picture and you could think of it in the following way. You see, what is the physics, and why do people? Sorry, let me just resize this. Yeah, you know, you could take this entire picture that we have and you could reduce it in the following sense. You know, on the left-hand side, you have gravity plus a CFTD in asymptotic ADS. But you see, you could reduce this asymptotic ADS using some holographic duality to the following setup. And here you have a CFTD with no gravity on a half plane. Okay. And on the left-hand side, you can take the entire system, which has gravity, and you can just replace it with some CFTD -1 that lives on the boundary of ADS. Okay. So what we have here is a CFT which just lives on a half plane. So we don't even have to say no gravity. It lives on a half plane and it ends at a defect. So this half plane ends at a defect. A defect, I just mean at a defect, by which I mean this. This is what I'm calling the defect, which supports a CFTD -1. This CFTD -1 is some other CFT. It's whatever the holographic dual to this theory of gravity plus CFTD is. Okay. So now if you think about this picture, the picture that I have on the lower part of the slide, like below the line, you see this picture doesn't have any gravity inside. There's no gravity anywhere, right? We have a CFTD -1, and there's a CFT it's the CFT which has a boundary. It lives in a space which has a boundary, and on the boundary there are some additional degrees of freedom. And this is the kind of setup that we've studied many times. Okay? Now think about this setup that I have on the lower slide. On this setup, let's just take an imaginary line. Okay. And this is some imaginary line. And let's look at the region to the left and right of the imaginary line. Okay. And let's call this region the radiation region. And this region to the left, the black hole region. But now in this setup where you have no gravity, it's clear that the Hilbert space factorizes, right? This is just an ordinary quantum field theory. And if you take this picture that I have here, it's completely clear that the Hilbert space factorizes. And therefore, I should expect to see a page curve as I do for ordinary systems. You know, there's just no gravity here. So let's draw this. So let's forget about, you know, if you just forget about the fact that the CFTD -1 had also a gravitational dual, you see there is no gravity here. And in this non-gravitational system, sorry, I'm trying to do things which I clearly am not capable of doing, making all sorts of changes of thickness and so on. But okay, in this non-gravitational system, and it's important that it's a non-gravitational system. The Hilbert space factorizes, and therefore, if we say that what is to the left is what we are calling the black hole, and what is to the right is what we are calling the radiation, it's clear that you expect that if you couple these two and you have some flow of information from this, if you start with a state in which this CFT d-1 carries energy and is in an excited state, then you expect clearly that you will see a page curve for the black hole region or for the radiation region. So let's say you compute the entropy of the radiation region, you expect you will see a black hole. So the setup that we have here is a setup where you've taken maybe n equal to 4 Yang mills or something else, you've cut it off at one point, and then you've added some defect. And now in the system which just lives on your tabletop, you're asking what is the radiation, or what is the entanglement between one part of the system and the other part of the system. Okay. Now, this page curve is therefore answering a non-gravitational question, but one can compute this entropy using gravitational holographic techniques. Okay. So let me just make a few comments. So in this setup, it's clear, as I said, first of all, that the Hilbert space will factorize because there is no gravity in the place where we make the division between what we are calling the black hole and what we are calling the radiation region. And so none of the effects that we are talking about are relevant at all in what we are in this setup here. And in this non-gravitational region, it's clear that we expect the page curve. But the interesting thing about these questions is that the page curve answers a non-gravitational question, but which can be answered using gravitational techniques. But the interesting part is that this can be answered using gravitational techniques. This is not something that we've seen for the first time in ADS-CFT. This is something that we have seen in many other situations previously in ADS-CFT. There was, for instance, a lot of development in the ADS-CMT literature and the ADS fluid dynamics literature. In ADS-CMT, we would say, well, we compute, for instance, the conductivity. Okay? And the conductivity is given by, some Kubo formula. So it's given by some 2-point function. There's some limit you need to take. And you compute a 2-point function, and there's some Kubo formula for the conductivity. You can define some conductivity in the non-gravitational boundary theory. But then you can compute this 2-point function using gravitational techniques. Using gravity as a tool. So what we are computing is not the conductivity of a black hole. I mean, you could say you're computing the conductivity of a black hole, but what we're really computing is something that's well defined in the theory that we have on the boundary. So this is the flavor of an ADS-CMT kind of question. And then we use the theory of gravity in a very clever way to compute this quantity. And that is something which is very nice. The fact that you have a holographic dual gives you a computational tool to compute a quantity which is well defined on the boundary. So in this situation, we have a page curve which exists for this setup, which is just an ordinary non-gravitational setup. You have a conformal field theory, you divide it into 2 parts. But you can compute this by using the fact that there's a holographic dual to the CFT d-1. Okay. So that's the first comment. The second comment I wanted to make is that this is, of course, there's this principle of holography of information that we've been talking about is not relevant here because we are in a non-gravitational setup. But in fact, there's another sense in which this whole thing is completely consistent. You see, let's replace back this CFT with this ADS, right? So we have ADS plus we have gravity plus matter here. Plus matter. Here's our CFTD, and here's our imaginary line, right? Now, there could be a black hole in the bulk. So maybe there's a black hole here in the bulk. But what does the principle of holography of information tell us? The principle of holography of information tells us that at all times, the information is in fact available here. So it tells us that the information is always available here. At all times. So even if there's some black hole in the bulk, the information always lives close to the ADS boundary. And therefore, this page curve that we are computing can also be thought of as information transfer from this region across this imaginary line in the non-gravitational bath into another part of the bath. So in this sense, it's completely consistent with the fact that the information is always outside the black hole. Okay? So this page curve the second comment I wanted to make is that this page curve can also be interpreted as information transfer from the near boundary region where we expect that information is always there to the non-gravitational path. Okay. So I think this is an important point because the words that go along with these computations sometimes say one is computing the page curve of a black hole with the radiation, but the division between the systems is never made at the black hole and its radiation. It's made across this non-gravitational region, and therefore the fact that the information is always outside is completely consistent because the information could always be at the boundary of the region where gravity is dynamical, and you would still see a page curve because you're just computing information transfer across this imaginary line where there is no gravity. Okay. So this is the second comment. Let me just make a third comment about this, and then we can stop. As I said, I think the island computations are nice, and we'll spend some time discussing them in some detail. But I think that one thing that we, at least one should be careful about, is that the diagrams that are drawn sometimes to describe the computations look like this. Okay, that we have a black hole, and then the black hole is coupled to an asymptotically flat region. Okay. But it's important that in these computations, to see the page curve, we need no gravity. And this is not the same as a setup which would be appropriate for a black hole in asymptotically flat space, where you would like to say that you have weak gravity. I mean, weak in the sense just that you're far away from the black hole. And the reason these two setups are not the same is what we've been discussing many, many times. It is that for fine-grained quantum information questions, and in particular for fine-grained questions like the von Neumann entropy, weak gravity is not the same as no gravity. Okay. And that's because the presence or absence of gravity changes some issues, such as the issue of the factorization of the Hilbert space, which we discussed at great length. And it could change the answer for what you expect for the entropy in a very dramatic way. And therefore, while the calculations that have been done are correct and interesting, they apply to the setup on the left, which cannot be generalized to the setup on the right. The answer for the setup on the right, at least if you were to compute in the simple way as I described in the earlier part of this lecture, would be different, and it would be more akin to a situation where the information is always outside. So we'll discuss this in a little more detail when we return after the break, but we're out of time. So let me stop here and let me see if there are questions.
I have a question about this. So yes, so this is about the MT-ADS monogamy violation. So yesterday, I think to respond to a question, you said that we are sort of cheating when we say that A and B regions are actually independent degrees of freedom, in the sense that those the algebras don't really commute, and the commutators are actually suppressed by I guess some order of G itself. Was that what you said?
Yeah, we are cheating when we said these A and B regions. Yeah, that's correct.
Right, right. So operators in those two algebras will actually not commute, and the commutators will be of some order of G. Is that correct?
You're talking about A and B?
Yeah, A and B.
Yeah, correct.
Right. Okay. So my issue is this. So if the non-commutativity of A and B algebras is of the order of G, then why isn't the violation of monogamy also order of G?
Because A and C is not order of G. A and C is order of 1, and B and C is order of 1. So the operators we constructed in C, they have non-zero commutators with B. In fact, the operators we constructed are such that CB is of order 1.
Right, right, and CB and C are order 1 because
you inserted this projector on the vacuum and so on. So CB is order 1, but AB is small. AC, I don't know, but AC we would have to estimate. But CB is certainly order 1.
I'm sorry. Could you explain once again why CB would be 1? Is it because of holography?
No. You see, we constructed these operators in a particular way, right? Remember that CI on remember that CI on the vacuum was like BI on the vacuum,
right.
And so you could estimate what C and B is, and CB would be large. I mean, that's the reason you're getting this. The fact that you're getting this larger than 8 is telling you that there must be some operators here which don't commute with each other. And the operators which don't commute with each other, I mean, you can try and estimate the commutator of C and B, but we had some construction for C somewhere in the previous slide. I don't know where I wrote it. Here. Yeah. So you could take this and you could just try and estimate what C and B is. And remember that B1 and B2 cannot commute with each other, right? Because otherwise we wouldn't get CAB larger than 2. So you would probably need to compute the commutator C1 B2 and C2 B1. And I think you could use this formula to compute the commutator, and that is what is order 1.
I see. Right, but these BIs are actually you have some QI also, I guess, which is actually created with operators in the C region.
There was a QI as well, yes. Right. But it stops commuting once you add this P0 in here.
Right. I'm sorry, I'm not catching why P0 won't commute with BIs.
P0 doesn't commute with the BIs because BIs have energy, right? So P0 BI is clearly non-zero. P0 is 0, 0. So P0, so the BIs have some energy. So P0 and BI is non-zero.
Right, but why wouldn't they commute?
Because if you act with P0 first or P0 after BI, it's totally different. Right? Yeah, BI adds some energy. So if you're in the vacuum in the first place, for instance, P0 in the vacuum would be 1, but P0 on BI in the vacuum might be 0.
Got it. Okay, thanks.
Okay.
I got two questions about the last part. Sure. So am I right that we are that it actually gives the wrong idea to divide between black hole microstates and radiation microstates in the CFT picture, right? We called this the black hole region and the radiation region, but
these are not black hole microstates. I mean, you could think of them as states of the CFT d-1, but if you think of the original picture here, here you have the black hole plus its radiation, right? So you have black hole plus its radiation plus all sorts of degrees of freedom, and you've combined all of that into a CFT d-1. So really the precise way to think of these computations is you have a non-gravitational CFT d-1, and which is coupled to another non-gravitational CFT d, and you're just computing. I mean, the question you're asking is best phrased just in a completely non-gravitational setup. I mean, we can, and to call this the black hole region is the same sense in which we say, when we compute the conductivity in ADS-CMT, we are computing the conductivity of a black hole, which, I mean, in a sense, is okay. These are terms which are often used in the literature. But the definition really is that you have the CFT d-1 and you're computing the entanglement of all of its microstates with the CFT d. Actually, CFT d-1 plus a part of the CFT d with the rest of the CFT d.
Yeah, okay. And purely, if we look purely at the quantum mechanical picture or the CFT picture, then wouldn't we expect a saturating page curve then? Or because it now goes, you drew it like it goes down now, but
I was not precise enough with that. It depends a little bit on what the precise setup is. In the last diagram I drew, you would expect a saturating page curve. But in this setup, as I drew, you could start with the CFT d-1 in an excited state. And you could just put in like a lot of energy here. And then that energy would like flow across this non-gravitational region into the CFTD. And at, in the beginning, the entropy of the CFTD, this part of the right in the imaginary line would be 0 because there's no energy. And after some time, it would be 0 again because the state is pure. It depends a little bit on what the precise setup we are computing is. But you could certainly arrange for a situation where you just have a page curve that goes up and down. I mean, in some other setups, which we'll discuss later, you could have a page curve that saturates, depending on how time evolves. But in a non-gravitational setup, if you just have some energy in this room, which flows out of this room, you will see a page curve, which is conventional. And that's really what is happening here. But you're right, you need to be a little bit more careful about what exactly time is and how time is evolving, and what the systems are to explain, whether you see a saturating page curve or not. But in the situation where the CFTD just has infinite volume and you start with the CFTD-1 in some state with energy, you would see a page curve which goes up and down.
All right, thanks.
Are there any other questions?
I might have one more, or
yeah,
maybe.
Sure.
Yeah. This was about the hierarchy. This just out of interest, but aren't there hints for this from string theory for the black hole microstate, that there might be some hierarchy there? I don't know.
Yeah, so the question is, if we were to identify the set of black hole microstates, you could then ask this question. Let's say you try to identify the black hole microstate. So the question we're asking was this one. Let's say you have a small black hole and you try and determine the microstate using these kinds of correlators that we have here. If you did have a precise description of what small black holes were, you could estimate, how hard or how easy it is to determine the microstate. And then maybe you would be able to answer how this difficulty changes with time. We do have there's some progress on understanding how small black holes should be represented. But I don't think we have a good understanding yet to be able to answer this question of how the difficulty changes with time. But it is a well-defined, precise question in ADS CFT that one can ask. It's just as I think you said, it's an issue of, you could also maybe frame it as a question of complexity, which is similar to this question of, how the difficulty changes in reconstructing the microstate. I don't think we have a good enough understanding to be able to answer this question. I mean, there's some progress in understanding small black holes, but yeah.
Regarding this hierarchy, I also had a question. Imagine you would want to reconstruct the microstate from collecting the radiation in case of a black hole. Then you would still see a page curve, right? Just the question whether reconstructing the microstate from this radiation is easier or harder than reconstructing it.
Now, actually, it's a good question. You see, it's not clear what you need to measure in order to be able to see a page curve for small black holes. There's another interesting question here, which is what are the CFT correlators you should measure in order to see a page curve? Clearly, if you measure all CFT correlators, you would just see no page curve. You would just see the flat page curve. You'd see the information was always outside, right? If I allow myself to measure, if I just look at the von Neumann entropy of a cut on the boundary, that von Neumann entropy is just clearly 0. It doesn't change with time. So when we say we want to collect radiation and measure the page curve, in some sense, you want to disallow some set of observations, right? You want to say that, I mean, here we're talking about difficulty. So somehow you want to say that, let me make all observations up to a certain level. Like, let me measure generalized free field operators up to some polynomial level. And then maybe I'd see the page curve. But in fact, this is also a question we don't know the answer to. In what sense do you expect to see a page curve for small black holes in ADS? I think it's far from clear what the answer is. If you want to see the entropy 0, it's clear what the answer is. You just include all operators in your algebra at all times. You'll see the entropy of the CFT is just CFT stays in a pure state at all times. So that's like this curve you drew, the flat page curve. But if you want to see a page curve that goes up and down, it's not clear what that curve should be. You probably can find some algebra which will give you the page curve. Right? But, if you insist that you want to see the page curve, you can always kind of vary in question space to see the page curve. But the more interesting question is there a natural algebra as a function of time which sees the page curve for a small black hole in ADS? And I think the answer to that is not known.
And then how would this all work if you choose to collect the radiation inside of the system?
Sorry, can you say a little bit more? I couldn't hear clearly.
Sorry, I was wondering how the answer would change if you would decide to collect the radiation inside of the system, so inside the ADS space, rather than in a space connected to it. They do not have access to the boundaries, so they do not have access to the.
That's what I just said. If you say if by collecting radiation, I mean you have to define clearly what it means by collecting radiation, right? We've been saying in the question I defined here, there was a sense in which this is a precise question that you measure all correlators and then you measure them at time t2 and time t3. When you say you want to collect radiation and you don't want to measure gravity effects, what does that really mean? The gravity effects live in correlators of the stress tensor, which you do need to measure because there are dynamical gravitons. And so in ADS, it's very hard to say, I want to measure this set of correlators, but I don't want to measure stress tensor correlators, because if you measure some set of correlators, the stress tensor will appear inside the OPE. So there's no clear algebra of operators that corresponds to collecting radiation without also taking into account these gravity effects. So collecting radiation is actually not a very well-defined term in ADS. It might be a better defined term in flat spaces, as we'll discuss a little later. But in ADS, it's not a very well-defined term. And so, because what does it mean to collect radiation? If you say, let's say you say, I'm going to measure all operators except for the stress tensor, because the stress tensor corresponds to gravitons. So you could start by doing that. But if you measure, the stress tensor always appears in the OPE of some operators. So you look at the OPE of two operators and the stress tensor will appear. And so if you start measuring these endpoint correlators, you will effectively also have information about stress tensor correlators. So there's no clear way in which you can throw away these gravity effects. They're kind of always there. And so in ADS, the most natural answer is that the information is always outside. And if you want to find a way in which you want to see the information emerging gradually, that is what one needs to work hard for. And it's not something which is known how to do. Is the answer clear, or should I elaborate more?
It's clear if I look at it from a CFT perspective, but I think the flat space is in that sense more interesting indeed, because they do not have the CFT perspective. Right. You really only have the bulk perspective, so to say. So in the bulk perspective, there is no you can't refer to the holographic information, so to say, because you're in the bulk.
Just to say, in the reason the flat space is more interesting is because there is a sense which I didn't describe, in which you can so there are this set of operators which live at future null infinity, which are the Bondi mass and the Bondi news. And in fact, there's a sense in which you can define an algebra of the Bondi news operators and never talk about the Bondi mass. And that's a precise sense in which you can say, I'm going to ignore quantum gravity. I'm going to ignore these funny gravity effects that localize information unusually. And that's because of an unusual property of null infinity, which is that, if you just look at the algebra of the news operators, the Bondi mass doesn't appear. That's a consistent closed algebra. And that property you don't have in ADS, because the ADS boundary algebra is more complicated. It's not the algebra of a Fock space. And so it's so there's some technical difference why it's easy to define what you mean by collecting Hawking radiation in flat space, and not so easy to define what you mean by collecting Hawking radiation in ADS. And that's why I framed this in terms of the difficulty of reconstructing the state by measuring Heisenberg operators, rather than talking about one set of correlators which correspond to collecting Hawking radiation and another set of correlators which correspond to using these quantum gravity effects.
But this is still from a perspective from scri-plus, right? So how would it look if you say you have a black hole around the origin, right? And you build a sphere around it, and on this sphere you try to collect the radiation.
Okay.
Scri-plus.
I agree. So there's again, excellent. So now you could say, let's say you make this Dyson sphere around the black hole and you make measurements. So you see, you have to be sensitive to metric fluctuations, right? Because otherwise you would never get information. So your Dyson sphere in which you're making measurements has to be able to measure quantum fluctuations of the metric. Otherwise, you'd never be able to reconstruct information. So if you start working in the bulk, then once again, the distinction between having a detector which is sensitive to collecting Hawking radiation and having a detector which is sensitive to these metric fluctuations is very hard to make precise. Because your detector, which needs to collect Hawking radiation, also needs to measure, metric fluctuations. And if it does that, it'll have the information at all times. So it's a surprisingly difficult question to answer. What is the detector that will see information according to the page curve? But in a sense, it's not even clear that that's the most interesting question. The question you want to ask is, let's say I make a detector with some physical capabilities. If it just sees the information is outside all times, then that's the answer. It's not. We don't have to then work harder to see what could you make the detector forget, or how could you close your eyes in a way to see the page curve. I think the interesting physical questions are the questions of what is the difficulty of reconstructing the information from the bulk. And if you could answer that, and if you find that difficulty doesn't become easier with time, then you would say the information is always outside. If it does become easier with time, then you would say the information emerges gradually.
Thanks. This clarifies a lot for me. Thank you.
Okay, thank you.